Thanks everyone for coming to our second talk for this semester's Student Colloquium seminar. I'd like to introduce Dr. Clayton Shonkwiler. He's an assistant professor at the Colorado State University. He got his PhD from the University of Pennsylvania and went on to do a postdoc at my alma mater, UGA. And I think he did an RU at LSU back in so it's good to have you back. All right, he's going to tell us about geometric perspective on random walks with topological constraints.
So thanks. Thank you for the introduction. Thank you for having me back. It's, like you said, I was here at an RU in 2002, and then I was here briefly to give a talk 2 years ago, but then I'm happy to be back again. So yeah, so I want to talk about like the title says, a geometric perspective on random walks with topological constraints. And let me just dive into the basic question. So a lot of people really care a lot about polymers because, of course, polymers are everywhere. DNA, RNA, proteins, nylon, polyester, plastic, picket, it's probably a polymer. And so if you're interested in things like biopolymers, so DNA or proteins, they're sort of floating in some solution. And then there's this sort of principle in the biomolecules community that the shape of a molecule determines its function or is very, very, very highly correlated with its function. And so one thing you have to come to terms with almost immediately is that these molecules, so polymers are these long, stringy molecules where you have, tens or hundreds or thousands or tens of thousands or millions of base pairs connected together by, simple bonds. And because although, at a micro level, molecules are very rigid, the bonds are extremely rigid, but because these molecules are so humongous that at the sort of a global scale, they're extremely flexible. They can bend and they're constantly being deflected by water molecules in solution, and so they don't really have a shape. They have sort of a ensemble of shapes or kind of an average shape. And so really, you have to come to terms with the idea that the things you're studying don't have shapes, they have sort of statistical shapes. And you can have very simple, topologically simple things which are called linear polymers. You can have more complicated situations where, for example, this is a loop of DNA. So this is an example of a plasmid, which are used in gene therapy in various places, where the ends actually come together and it forms a closed loop. And obviously there you actually have interesting topology going on. Or you can have, in polymer melts, like in your contact lenses, that's an example of a polymer melt. Rubber is very similar to a melt in various ways. You have lots of these molecules stuck together in really interesting and non-trivial ways. And so the basic paradigm, to use one of many buzzwords, is that you think of a polymer as being more or less a random walk. And people have gotten a lot of, this is sort of the Flory idea from back in the 60s and 70s that, you should think of a polymer, at sort of a very sort of gross level as being like a random walk. And so the analogy is that, as the ideal gas law is to actual gases, random walks are to actual polymer chains. So it's a very idealized model, but it's still sort of the standard starting point for people's models. So here's an example. So when I say I'll say what I mean by a random walk a little more carefully in a minute, but here's an example of a random walk with 3,500 steps. And you see that they tend to have this sort of, there's some sort of longer, straighter bits, and then there's some big clumpy bits, and then sometimes you have bridges between the clumpy bits that are sort of longer and straighter. But this is sort of the picture that you tend to see with these kinds of things. Okay, so here's the big idea, in my opinion, so people, of course, have been thinking about random walks for 100 years, and thinking about random walks in connection with polymers for 50 years. But a lot of that work has been really very probabilistic and very analytic and not so much geometric. And so my claim is that a really nice way to understand random walks and make progress in new directions is to think of random walks as being points in moduli spaces, and then to do geometry and topology on those moduli spaces to help you understand random walks. And the other sort of big idea that is maybe not written up here is that ideally your moduli space should have lots of symmetry. So you're also hopefully going to have big symmetry groups acting on these moduli spaces, and again, in the usual way, that's going to help you understand what's going on. All right, so that's the idea, and then the objects are what I'm going to call topologically constrained random walks, which means, so you take some abstract graph like this guy, and then you say, okay, well, I want now a collection of random walks which collectively, form this abstract graph. So here I've shown, so you have the black loop, and then you have these three, the red, the purple, and the green edges. And so over here, the black loop is actually 21 edges, and each of the red, green, and purple, I think, are 7 edges. And it's maybe a little bit hard to see, but you see that those three colors come together at this point, which is that point, and otherwise they just meet up with the black loop over there. Yeah?
Each point is actually a random walk.
So this green segment is what I'm calling a 7-step random walk. And this red segment is a 7-step random walk. And this purple segment is a 7-step random walk. And this black thing is a 21-step closed random walk, so it closes up to form a loop. So, but then then this in turn is going to be a single point in some gigantic moduli space, is the idea. Yeah. So, yeah. All right, and here's just one example of where these things actually come up. So this Tezca lab just a year or two ago actually created a synthetic K3-3. So this is the complete bipartite graph on 3 and 3. And so that's abstractly what it looks like. And they did this horribly complicated chemical reaction to actually generate something that has the topology of a K3-3. This is like polystyrene or something. And the lengths they went to, they had to do sort of 17 iterations of their, culling things out. Like they get a lot of byproducts, and they had to do 17 iterations of the purification process to actually get the guys that they wanted. It was really just sort of an amazing experimental result to produce one of these things. And the reason people want to do these things is that if you can create polymers with interesting topology, the idea is that the topology should inform their material properties, and so hopefully you can create materials with interesting and useful properties. Okay, so fine, we want to understand topologically constrained random walks, and then you can ask a bunch of questions like, well, if you're topologically constrained, you have to, the steps in your collection of random walks have to form a predetermined graph, then the steps are not independent. They're constrained in this sort of weird way. So what is the joint distribution? It's not a product distribution, it's a multivariate joint distribution. What is it? What can you prove about it? I guess these two questions are really the same thing in some sense. This radius of gyration is just the mean squared distance to the center of mass, or equivalently the mean squared vertex-vertex distance. And that's something that can actually be measured in physical polymers using scattering experiments. So this is something that physicists really care a lot about is, well, what, for this thing, for the K33, how they actually recognized that they had what they thought they had was they computed the something related to the radius of gyration and saw that it matched very closely to the theoretical model of what it should be, and therefore concluded that they had actually synthesized what they thought they had synthesized. This constitutes proof for physicists. Something else that the biomolecules people care a lot about is, well, what knot types do you see and in what percentages? If you have a 1,000-step, random walk that forms a loop, how likely is it to be an unknot? How likely is it to be a truffle knot? How likely is it to be a composite knot? because knotting has sort of interesting biological properties. So it's really interesting to understand those things. And of course, these types of questions quickly get really, really hard to answer theoretically. So you also want good numerical techniques so you can just simulate these things and at least, empirically say, well, we know what the answer is even if we don't know how to prove it. We can do a Monte Carlo integration and at least know more or less what the answer is. And ideally, you want sort of sampling techniques that give you good error bounds with known convergence rates and so on and so forth so that the answers you get actually mean something. So that's sort of the things that we want to do is prove theorems and also create, sort of statistically valid sampling algorithms. So that's sort of the general setup of, what people want to do in this field. Okay, so now I'm going to specialize a little bit to the second simplest case. So the simplest case is just a completely unconstrained random walk. So you just say, okay, well, I'm just, supposed to, this is not really a constraint. You're just saying, like, I have a random walk, and it has a starting point and ending point, and I don't really care where those are. So that's well understood because the steps in your walk are going to be independent, and you can sort of understand that really well. The next simplest thing you could do is to form a loop. So now, of course, this is a global constraint. You have to get back to your starting point, and so now you've lost all kinds of independence. And so we call these things closed random walks or random polygons, and they model these ring polymers. So here's, I think, the first observed example of knotted DNA. And then people are really interested in using DNA minicircles for gene therapy because they're much safer than plasmids. And so people are doing a lot of both actual experiments and numerical experiments with DNA minicircles. And so this is from one of those simulations. Okay, so before I showed you a random walk with no constraints with 3,500 steps, here's a random walk with this closure constraint that it gets back to its starting point after exactly 3,500 steps. And you can see sort of at a gross level it has the same sort of behavior. You have the sort of long stringy bits and then the clumpy bits and so on. Okay, so that's sort of where you want to get to is can you simulate these random walks in 3 space because that's where molecules actually live. Yes?
Do you allow for the segments to pass through each other?
Yeah, so the answer is yes because we don't know how to prevent it yet. But of course, in actual polymers, these things actually have thickness, and so of course they can't self-intersect. And in fact, they can't, if you're thinking of the curve as sort of the core of the polymer, they can't actually come closer than epsilon away from each other. But incorporating that constraint makes things much harder. But that's what you want to do for sure. But in everything I'm talking about today, I'm allowing self-intersections. I'm not. Of course, it's probability 0, but Okay, so to build up, let's start out just talking about planar things. So instead of polygons or random walks in 3 space, think about random walks in the plane. So a random walk in the plane, I should have put a picture on here, but I'm just saying, okay, you take you have some starting point, you choose a direction, you sort of uniformly at random, you take a step in that direction, maybe a unit step, maybe according to some length distribution, depending on the situation. Now you're at a new point, you choose a direction at random, you take a step in that direction, and you just keep iterating. So that's sort of a classical random walk, is you're just choosing these step directions randomly, and you're just taking steps independently of each other. Okay. Now the first thing is that what we care about is the shape of these random walks. So you really want to mod out by rigid motions. So for example, you don't care if it's based here or based over there. You want to mod out by translations. And a really easy way to do that is instead of focusing on the vertices, to focus on the edges and think of the edges as vectors, which I guess I'm calling W1, W2, W3, and so on. And of course, the nice thing about being in the plane is that vectors are complex numbers. So I'm going to think of my edges as actually being complex numbers. And now I'm going to do something a little bit weird, which is I'm going to take square roots. So I'm going to think of each of those edges as being the square of some number zi. It's not at all obvious why I'm doing this. So far I'm just doing it, and we'll see why later. Okay. So if these are the squares of a bunch of complex numbers, that list of complex numbers is itself a vector in complex n space. And if we're saying, okay, well, if the total length of this random walk, say, is equal to 1, then you're saying the norms of the squares of your complex numbers has to be 1. So you lie on the unit sphere in complex n space. So this tells you that if you're interested in just random walks with fixed total length, you're really looking at the sphere in complex n space. Okay. So this, in turn, you can say, okay, well, the sphere in complex n space is a nice round sphere. It has, the action of either un or O2n, depending on whether you want to think complexly or really. So it has Haar measure, and Haar measure is just the uniform measure on the sphere. And you can say, okay, well, I'm going to take that uniform measure on the sphere, and that's going to be my measure on these random walks of total length 1. And the first thing you should do is say, why would you do that? Does that make any sense at all? And the answer, in fact, is yes, it makes a lot of sense, because if I'm taking a walk whose total length is 1 and has n steps, then sort of the natural way to do that would be to say, okay, well, I'm going to take the directions of each step independently. So this direction is completely independent of that direction, and so on and so forth. And the only constraint is the lengths of the edges have to sum to 1. Well, that tells you lie on the simplex of numbers that sum to 1. And then it turns out that the uniform measure on the sphere is the same as taking the uniform measure on the simplex crossed with, the uniform measure on the product of circles, where you're just choosing your directions completely independently. So if you don't like this slide, you can ignore it. The point is just that this is sort of a natural construction, and the key to it was this taking the square roots business. If you hadn't taken the square roots, things would not have worked out nearly so nicely. Okay. Now, I said before that all we care about is the shapes of these things. We already modeled out by translation by taking edge vectors as a sort of our basic objects. But we should also mod out by rotations, because it shouldn't matter whether it's pointed this way or that way or whatever. So now if you want to mod out by rotations, it turns out that what you're really doing is you're modding out by this relation up in the complex n space. So you're saying, your vector is the same whether or not you multiply by some unit complex number. But of course, this is complex projective space, right? So I just so this construction I'm describing, I think I'll say on the next slide, is due to Hausman and Knudsen. And this is just amazing. You're saying oh, well, these random walks are really complex projective space, which is this beautiful Riemannian manifold. It's a complex manifold. It's a symplectic manifold. It's a projective variety, sort of trivially. It has all of this geometric structure, so you can translate any question you like about these random walks into geometric questions about this beautiful geometric space. Okay. So that's just for these chains. Projective space corresponds to these open polygonal chains. Well, now I said we want to do this topological constrained random walk business. So now instead of an open chain, we want it to come back to its starting point after exactly, n steps. so here's the condition. So remember, we took the square roots of each of the edges. That gave us a vector of complex numbers. And now I'm going to write that vector of complex numbers as real part plus I times imaginary part. And I'm just going to peel off the real part and think of that as a real n vector, and the imaginary part and think of that as a real n vector. And then the super amazing theorem is that your polygon is closed if and only if those two vectors are perpendicular and the same length. Okay, so, and the proof is like just a computation. You just say, oh, well, if z is a plus bi, then z squared is this, right? That's completely straightforward. So now, what does it mean to close up? Well, we're treating these things as vectors, so closing up means the vector sum is 0. Okay, so if the sum of these zi squareds is 0, that means the real part has to be 0, so the sum of the ai squareds minus the sum of the bi squareds has to be 0, and the imaginary part has to be 0. That means the dot product of the a vector and the b vector has to be 0. And then, so this length 2 condition, it just turns out that the total length of this thing is the sum of the square of the norm of A and the square of the norm of B. So if these are unit length, then the whole thing is 1 squared plus 1 squared equals 2. But you could pick your favorite scale factor if you want, and you just adjust these appropriately by scaling by the square root of that scale factor. Okay, so again, this is this amazing construction of Hausmann and Knutson's from 1997, maybe, something like that. Okay. So now, the collection of A and B that are orthonormal vectors in Rn, that has a name. That's an example of a Stiefel manifold. So in general, if I write VKRn, that's the Stiefel manifold of orthonormal K-frames in Rn. That just means I take a collection of K orthonormal vectors sitting inside of n-dimensional space, and all possible such things are exactly this manifold VKRn. So the Hausmann-Knudsen theorem says, well, if you're taking closed planar n-gons with this length factor, then you're exactly talking about this particular Stiefel manifold, which is pretty cool. And even better, again, you want to do the business where you say, oh, well, if I want to mod out by rotations of the plane because I care about the shape of these things and not their particular orientation. So it turns out, okay, you have your two vectors, your A and your B vectors, sitting inside of Rn. A natural thing you can do is just rotate within the plane that they span. You have two orthonormal vectors. They span a two-dimensional plane. You can rotate within that plane. And by construction, the end result is rotating the corresponding polygon twice as fast. So if you rotate these two guys, clockwise within the plane they span, you're rotating the corresponding polygon clockwise but twice as fast. And the twice as fast is because you had this squaring business going on. And of course, when you square complex numbers, you double the angle. Okay, so we said closed n-gons are like the Stiefel manifold. And now if we do a rotation to a Stiefel frame, and we just mod out by that rotation, you're saying, okay, well, I don't really care about the frame. I just care about this plane that it spans. And the collection of planes in Rn of dimension k in general, but dimension 2 in this particular case, is another very famous manifold called the Grassmann manifold, which is even better than the Stiefel manifold because it has, it's more of an algebraic object than the Stiefel manifold. So now our polygons, again, of this fixed length scale, but now we've modded out by both translations and rotations, is the Grassmannian of two planes in Rn. So I just want to take a step back and say a little bit about Grassmann and Stiefel manifolds. So these are really some of my favorite manifolds in the world. I would say 30% of my PhD thesis was just computing a particular example on a particular Grossman manifold. So I've grown to know and love these very much. And of course, there's lots and lots of papers talking about all different things related to Grassmannians and Stiefel manifolds. And so, for example, the Grassmannian of K-planes in Rn, you can think of as a homogeneous space. So you certainly have an ON action. You just think of these, these are K-dimensional planes in Rn. You can multiply by, an ON element. And you divide by OK cross ON minus K. Well, the ON minus K is what's acting on the orthogonal complement of the plane. And the OK is what's acting on the plane itself. And of course, if you act on the plane itself, you're not changing the plane at all. So it's pretty easy to see that this is a homogeneous space in this way. Of course, from here, since you know the dimension of the orthogonal group, you can compute the dimension of the Grassmannian, and it turns out to be K times N minus K. And you can compute the volume. It's basically a product of volumes of spheres. I guess this is repeating what I already said. You have this transitive ON action, and therefore, in particular, again, you have a big symmetry group, and you have a really nice measure, so the Haar measure. So for those of you who aren't measure theorists, Haar measure is just the unique measure which is invariant under the action of your transitive group, right? So it's very often the best measure. And the homology groups, not homotopy groups so much, but certainly the homology groups and lots of other things, the cut locus, all different things are unknown about these manifolds. And so in particular, if we look at this line here, well, we're interested in G2Rn, so it has dimension 2 times n minus 2, so 2n minus 4 dimensional, this space of closed n-step random walks of total length 2. Okay, which makes sense, right? Because you have n steps. Each step in principle is sort of a two-dimensional object, so that's your 2n. But you mod it out by translations, which is 2 dimensions. You mod it out by rotations, which is 1 dimension. And then you fix the length scale, which is 1 more dimension. So that's another way to see the 2n minus 4. All right. So here's an application of this gigantic theory to an old and kind of nice elementary problem. So if you look at pillow problem number 58 from Lewis Carroll's book of pillow problems, he asks, okay, you take 3 points on the plane, what's the likelihood the triangle that they form is obtuse? Now, of course, the question as asked is not well posed, right? Because what the heck do you mean choose 3 points randomly on the infinite plane, right? There's no uniform distribution on the plane. You can take them according to a Gaussian, but why would triangles care about Gaussians, distributions of their vertices? So there's this wonderful paper in, I think, The Monthly by Stephen Portney, who says, the basic problem is, what do you mean take a random triangle? The space of triangles doesn't have a nice symmetry. It doesn't have a transitive group action. Well, but, we just said there is a transitive group action if you take this Grossman model. So in our model, well, there's your transitive group action, this O3, which acts on G2R3. And of course, G2R3 is one of our favorite spaces. It's RP2. Well, RP2 is less of our favorite space than S2 if you take the double cover. And then, well, everybody understands S2 pretty well. And you can just draw this picture and see that, well, the acute triangles under this identification between triangles and this double cover by S2 are exactly these 8 sort of weird, coincidentally triangular looking shapes. And the volume or the relative area of the complement of these gold shapes is exactly this. So you get that the probability of being an obtuse triangle is exactly this number, or roughly 83.8%, which I think is super cool. No, Lewis Carroll's answer was something like 68%. But what he did was he took 3 points uniformly on the unit disk, which doesn't strike me as a particularly useful way of choosing random triangles, but there you go. That's what he could do, at least. I should say there are other answers. There's Lewis Carroll's answer. There's also, if you take 3 points according to Gaussians, you get something like 75%, and there's a few different proposals. But we like ours because you have this transitive group action. And also because of this fact, so what do you know that side, side, side determines a triangle. Now, of course, obtuseness doesn't care about, if similarity. So if you rescale, you don't change the obtuseness. So you might as well fix a scale. So fix your scale to be 2 because that's what's convenient with the theory. So now you say, okay, well, what's a triangle? Well, you just have to choose your 3 side lengths so that they sum to 2, and that uniquely determines, a similarity class of triangles. And so you can also, then you get a map from this sphere, this triangle space thought of as a sphere, to the simplex of things that sum to 2. And if you do that, sort of the uniform measure on the sphere pushes forward to a density on the simplex where the density is exactly 1 over the area. So the fact that the density is 1 over the area after you've gone through all these contortions means that really, or we claim that it means that you're capturing sort of a really geometrically natural measure on triangle space. Yeah?
So you're putting a probability measure, a probability on triangle space,
Yep.
so not on the underlying points. And wasn't Lewis Carroll's original problem, doesn't it say?
Yeah, sure.
And what's the probability?
Yeah.
Result?
But I claim that his question is asked can't be answered. Like there is no answer to his original question.
No, yours, you have the sum being 2.
Yeah, but
So you're still in a certain particular class of triangle.
well, but again, I'm just picking a scale because I want to mod out by similarities.
Okay.
I just want, one way to think about it is I want my space to be compact, so when I integrate, I get an answer.
So you can apply, okay, so it's the same answer for all lengths.
Yeah. So if I chose length 27, I would still get this exact same answer here. Yeah. But, I'm not saying this is the definitive answer. I'm saying this is a nice answer, and, we think it's a good answer, but you may disagree. And that's fine. Okay. So that's sort of the story for planar things. So it's sort of developed by Hausmann and Knudsen, and then you sort of interpret it in this way. They're getting back to the question about polymers. Now you want to take these polygonal walks not in R2, but in R3. So in R2, you got to take advantage of the fact that R2 is C, and you could really do sort of algebra and get the answer. R3, of course, is not naturally a number system in a very nice way, but of course the quaternions are. So what you're going to do is you're going to use the quaternions. So just as a reminder, or an introduction, very brief one, to those that haven't seen this before, the quaternions consist of numbers that look like A plus BI plus CJ plus DK, where I, J, and K satisfy those conditions, right? And the annoying thing is that it's non-commutative, because if you take I times J, you get K, but if you take J times I, you get minus K. So everything, it's a skew field, but it's not a field because it's not commutative. And then there's this, first semester graduate algebraic topology question about, well, why does S3 form the double cover of SO3? And here's the answer. Sorry, whoever's teaching that course and wanted to ask that question. But the point is, okay, S3 is the unit quaternions, right? And so if you plug in a unit quaternion, and what you get out is a 3 by 3 matrix whose first column looks like Q bar IQ, second column Q bar JQ, and so on. So it turns out that these 3 are all purely imaginary, so they have no A components, so you can think of them as vectors in R3. And then the point is, well, the norm of this column is the norm of Q squared, but the norm of Q was 1, so that's still 1. And the fact that I, J, and K are perpendicular tells you that these 3 columns are also perpendicular. Okay, so now it turns out, this is the slightly unfortunate part of the story, that if you want to talk about polygons in R3, you really should talk about framed polygons. So now instead of edge, 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 I actually have frame, 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 frame. So I think of each of these edges as really being a 3x3 matrix with perpendicular columns where the norm of each column is equal to the norm of all the other columns. And the first column is the edge, and the other two columns are these perpendicular things, and then the first column is the edge, and so on and so forth. So the C just means I'm taking the cone over SO3 because I'm allowing the norms of the columns to be something other than 1. Okay. So now what you can do is you say, okay, well, I take a quaternion, I apply the Hopf map, that gives me a frame. So if I take a list of quaternions, I apply the Hopf map, that gives me a list of frames, which I can then think of as one of these framed random walks. And then again, well, what's the total length of this random walk? Well, it's the length of the first column of my frame. What's the length of the first column of my frame? Well, it's the length of qi squared. And so if the sum of these lengths is equal to 1, you're saying the sum of the squares of the lengths of the qi's is equal to 1. So again, you're talking about a unit sphere, but now in quaternionic space rather than complex space. And so this is basically the argument that this, again, is sort of a geometrically natural thing to do. If you take the joint distribution of edge lengths, you get what's called a Dirichlet distribution on the simplex. So let me just leave it at that and say it's something fairly natural. And then again, you say, okay, well, I have these framed random walks. I saw them as lists of complex numbers. Now what if I want to mod out by rotations of R3? Well, rotations of R3 are elements of SO3, but remember, elements of SO3 are like unit quaternions. So upstairs, I'm just dividing by the action of multiplication by a unit quaternion. And so what you end up with is quaternionic projective space. So again, a really wonderful manifold that people know lots and lots about. And the point is, well, if you want to answer questions about these framed random walks, you can just ask those questions in the appropriate language up in this quaternionic projective space where you have lots of tools to try to answer them. Okay. And then, so that's these open guys where you don't impose the topological constraint that they close up. If you impose the topological constraint that they close up, it's the same thing that we had before. The walk ends up being closed if and only if the vectors are the same length and perpendicular. And again, the proof is a computation, but it should be totally believable. Again, if you just write it out, this is what you get. Hopf applied to a single quaternion, where I think of the quaternion as complex number plus complex number times j, looks like this. And so if you want the sum of all the edges to be 0, you need the I part to be 0. That's saying the lengths of the A and the B are the same. And you need the J and K parts to be 0. That's telling you that the Hermitian inner product of the two vectors is equal to 0. So the upshot of all of this is that if you want to talk about these closed polygons, you're really talking about the Stiefel manifold. And if you want to divide by the action of rotation, then, well, you're dividing by the action of U2, where again, you take these two vectors in this complex 2 plane that they span. You rotate within that plane. That's the action of U2. And when you divide, you get the Grossmann manifold. Okay, so the upshot of this is that you've now accomplished what you set out to do, which is to think of your topologically constrained random walks as points in some really nice moduli space. This is the really nice moduli space. Okay, and then step 2 is use your knowledge of the really nice moduli space to start answering questions about the random walks. So this is just saying why this is such a nice space. Again, it has a Haar measure on it. And so the idea is to translate questions about random walks to questions about Haar measure on the complex Grassmannian of two planes. So here's an example of the sorts of things that people do. So, whoop, I didn't mean to do that. All right, so you have this closed walk, this a walk that you require to close up. Now imagine it had 1,000,000 edges. So, at each step, eventually you have to get back to your starting point. So, your choices are not completely unconstrained. When you say, I'm going to take a step in that direction, you say, well, I know I have to get back to where my starting point was, so I should be slightly more likely to take a step sort of back than forwards. But if you have 1,000,000 steps, you should feel that constraint very weakly. So the intuition is that, if you have enough steps, you should think that you're basically not constrained at all. So short arcs of closed things should look like short arcs of open things at sort of a measure theory or a probabilistic level. And this is what this theorem says. So this is just the definition of total variation distance. It says, well, the distance between two measures on a space is sort of the maximum difference between the measures they assign to two measurable subsets. So this is if two measures are close in this sense, they're close in pretty much the strongest possible sense, because you're taking the worst case scenario of where they differ. And so this theorem of Michael Berglund says that, well, okay, if I take a 1,000,000 step walk and I look at just the first 10 edges, then the difference between whether it's required to be closed or not is bounded by this. And when n is big enough, this looks like this number down here. So it's basically k over n. So if k is small and n is big, of course, this is very small. So this is, in some sense, not a surprising theorem, but still somewhat remarkable thing that you can prove such a quantitative theorem about how close these things actually are. And so in particular, what this tells you is that if you have some function on polygons that you're interested in that only depends on short arcs, you might as well just integrate over open things where you can probably figure out the answer because edges are independent there. So this is saying the expected value of some function that depends only on sort of k contiguous edges. For closed things and for open things, the ratio has to go to 1 as n goes to infinity. And so in particular, this theorem is about, okay, take the expected turning angle. So I have an edge, I have another edge, and to get from this edge to that edge, I had to turn through some angle. And of course, that angle is going to be between 0 if you just kept going in the same direction, or pi if you doubled back on yourself. And so what the theorem says is that, well, if you don't have any constraints, then of course you expect that you should have pi over 2 times the number of turns that you do. So total turning angle is just the sum of the turning angles. So if you have n turning angles, I take a sum of the n turning angles. Okay, so if you have no constraints, you should be just as likely to keep going this way as to double back going this way. And so on average, you should make a right turn, so a pi over 2. When you're closed, well, you know you have to get back to your starting point eventually, so you should turn slightly more than pi over 2. But the theorem is that, well, it's not so much more, right? So if you look at a single angle, you're going to divide everything by n, so it looks like pi over 2 plus pi over 4 times 2 over 2n minus 3. So it's pi over 4 times 1 over n, basically. And you can see that, of course, this and this, if you take the ratio and let n go to infinity, you're going to indeed get 1, as expected.
Oh, is that n in the numerator?
No, this is right. The point is, this is the total turning angle, so you're taking the sum over n angles, and basically the total excess is like pi over 4, but any particular one is like pi over 4 times 1 over n. Yeah. Okay, so if you're a student of Hermann Gluck's, you take this theorem and you say, okay, but this should tell me something about whether I'm allowed to be knotted if n is small enough. And so, in fact, this theorem tells you that no more than 2/3 of hexagons are allowed to be knotted, and no more than 10/11ths of heptagons are allowed to be knotted. And the proof is basically the Ferry-Milnor theorem. So by Finchel's theorem, you know that the total turning angle has to be at least 2 pi. Ferry-Milnor theorem says if you're knotted, it has to be at least 4 pi. And these numbers on the previous slide, when n is equal to 6 or 7, so if you look at this number and plug in n equals 6 or n equals 7, you get numbers that are less than 4 pi. So basically, if the average is less than 4 pi, some fraction has to actually be less than 4 pi. And so some fraction has to actually be unknotted. And this proof is just writing that out carefully. Which, I should say, this is like the only bound on the knot probability that's known for finite n where you have the, some hard explicit bound. Of course, so this is for very small n. Of course, hexagons and heptagons, because you need at least 6 edges to form a knot. If you only have 5 edges, you can't be knotted. That's another really cool theorem. Now, of course, there's this general idea that if you have a closed random walk with many, 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 many edges, it should be knotted with extremely high probability. So this was first conjectured not quite in this form. They just said that the knot probability should go to 1 as n goes to infinity. But if you have lots and lots of edges, the probability that an n-gon is unknotted should actually be exponentially small. So this has been proved in various models by Stu Whittington and DeWitt Sumners and Pippinger and Diao in sort of the late 80s and early 90s. Of course, the problem is there's no useful estimates or bounds or anything on what this alpha should be. But the hope, and maybe one of you can actually do it, is to take a theorem like this or maybe a stronger theorem and soup it up to actually get explicit bounds, quantitative in some sense bounds on what the alpha should be, at least in this particular model. Okay. So that's some sort of sampling. So these theorems are some sort of sampling of what theoretical things are known about these topologically constrained random walks. And I just want to briefly talk about the other thing that I mentioned, which is, okay, how do you do numerics? How do you do simulations? How do you, take something that can never, so if you look at 527-step closed walks, and you want to know what's the fraction of trefoil knots among those 527-step closed walks, you're never going to get a good theorem about that. At best, maybe you'll get some terrible bound, but you're never going to do better than that. In my opinion, I could be totally wrong, but I suspect not. But if you could do really good numerical experiments where we generated 100 million 520-step random walks and looked at the knot type for each of those and saw, okay, well actually we see that 12% of them are trefoils, then you could pretty much believe that probably about 12% are actually trefoils. So to do that, of course, you actually need a good numerics in that you're actually sampling these things according to the correct distribution, and B, it needs to be fast. Because if you want to generate 100 million of these things, you don't want to wait, a decade to do it. So this theorem says you can do both of those things. So remember, these polygons were basically points on the Grassmannian. Well, generating points uniformly on the Grassmannian is really easy. Here's how it works. You want random 2 planes in Cn. So generate 2 n-dimensional complex Gaussians. With probability 1, they're linearly independent. The plane that they span is uniformly sampled from the space of all two planes in complex n space, period. And if you want an orthonormal basis, just do Gram-Schmidt on those two multivariate Gaussians, and you now have an orthonormal basis. Okay, well, everything I just described takes linear in n time. Generating an n-dimensional Gaussian takes linear in n time. Doing Gram-Schmidt is linear in n. And so the whole thing is linear time, which is as good as you could possibly hope for. And so when you do this, here's some random 2,000 GONs. And I showed you earlier a random 3,500 GON. Yeah. So that's sort of part of the story. If you want to hear more of the story, come to my talk tomorrow in the Topology seminar, where I'll say a little bit more about connections to symplectic geometry and algebraic geometry. But let me leave you here with some open questions. So first off, linear walks, so just random walks with no constraints are easy, relatively speaking. I've just talked about, okay, if you form a loop, which is like the simplest possible non-trivial multigraph, right? You have one vertex and one edge. But now, what about more complicated graphs? What about theta curves? What about, the complete bipartite graph on three things and three things, right? Or even, the Peterson graph, or, pick your favorite graph. How do you, and say you pick your favorite graph, you specify how many edges, how many steps in the random walk should be along each of the edges of the graph. How do you then generate, a random walk that achieves that graph? Or how do you construct the moduli space of all such things? How do you prove theorems about such things? That stuff is still completely wide open. Another big thing, which, I'm going to talk about that in a second, so let me skip over to here. So I gave you two theorems about knotting. So one, this thing about, okay, well, hexagons, only a third of them, or at least a third of them have to be on knots. Heptagons, at least an 11th of them have to be on knots. And then there's these results of Sumners and Whittington and Pippinger and Diao that says, well, as n goes to infinity, the probability of being knotted, goes to 1 sort of exponentially fast. But that's basically it that's known theoretically about knotting in these random walk models. So anything one could do, like, well, what's the expected, what's the expected Casson invariant of a knot in one of these models? What's the, what's a lower bound, or say an upper bound on the probability of being unknotted when n is bigger than 100? Can you prove, so what you actually see when you do experiments is that if you say you look at trefoils, well, the probability of being a trefoil when you only have 4 edges is 0 because you can't be knotted if you only have 4 edges. And then what you see is that, well, the probability of being a trefoil goes up for a while as n increases. Maybe I should draw this on the board. So n is the number of edges. This is the probability of being a trefoil. And what you see is it goes up for a while, and then it goes exponentially down and tails off to 0. And you see this for every knot type that you try to do it for. But can you prove that this distribution is actually unimodular? It seems to be, but I don't know. Unimodular meaning it goes up and then it goes down and it never comes back up again. Can you soup all this stuff? So this is about, okay, piecewise linear closed one manifolds in R2 or R3. But what if you want piecewise linear closed surfaces in R3 or in R17? Or you want piecewise linear closed K-manifolds in Rn, right? Can you soup this up to deal with those sorts of things? So this business about self-avoiding random walks comes back to the question that was asked near the beginning, which is, well, in fact, real polymers have excluded volume constraints. Two vertices aren't allowed to intersect each other. Two edges aren't allowed to intersect each other. How do you incorporate that into this whole story? Okay, so I'm pretty much out of time. So let me just say that where the vertices actually collide. If you think about it, okay, you go out and then you have a vertex-vertex collision. That means you have a sub-polygon inside of your bigger polygon. You went out and you came back, and then you go out again, and then you come back again. Well, of course, if you have a k-step polygon, that's gk, g2ck, and then, of course, you have to go out and come back again, so you have an n minus k step 1. So the ones where vertices collide look like a product of littler Grassmannians inside of your bigger Grassmannian. Now you say, well, I don't just want to prevent vertices from colliding, but I want to prevent vertices from getting too close to each other. Then you're taking the complements of neighborhoods of these products of subgrassmannians, which I suspect algebraic geometers really understand, but I don't yet. So I would love to understand that much better. But that's all I have, so thank you very much for listening.
Are there any questions?
Yeah, so is there any physical reason why polymers should be modeled by these framed random walks as opposed to non-framed?
So, for example, proteins have a natural physical frame. And so there's some people that are actually trying to do work to see if the frames that you get here, does the Fernet frame mean anything in that language? Or, take your favorite frame, does that actually mean something in the language of proteins? Since these are actually molecules with thickness, really you think of them as like elastic rods or something. And so you have kind of a natural framing. But to date, that hasn't been incorporated into the theory, but that would, of course, be an excellent thing.
So the hope is that this is not, the framing you're doing is not just sort of a mathematical thing that allows you to do computations, but something that should have...
Right, so of course you can ignore the framing by just saying, well, we're just going to record the first, column of this matrix. And that's, in fact, what Hausmann and Knudsen did. And then somewhat later, Howard, Mannon, and Milson said, well, in fact, you get this sort of framing information. And so that was sort of like, oh, wait, there's actually more coming along for free, but if you don't want it, you can ignore it. So this business where I was taking, the expected turning angle, I was ignoring the framing because it doesn't matter for this turning angle thing. So you can keep it or forget about it depending on what you want to do. But the hope is that by keeping it, you can actually do things that aren't, are better than just random walks, sort of in a pure way. But yeah. Yeah.
I'm a little confused about how you generate random walks that end at the same place as the start.
Yeah, so the statement is that the machinery for doing that is you just need to choose a random n by 2 vector, or n by 2 matrix rather, such that the A vector is perpendicular to the B vector and the norm of A is equal to the norm of B. So the theorem is that that's all you actually have to do, and this is numerically easy to do. Why that is, well, that's sort of this computation that I was.
And n is the number of steps?
N is the number of steps, yeah. So if you want 527 steps, you would have 527 rows in this tall, skinny matrix.
And on that, and this is also why it's harder to figure out, like, if you want to constrain by other multigraphs, then we don't have a formula. There's no necessarily proof that works in the same way.
Yeah, I mean, the short answer is we just don't know what the appropriate geometric object is yet. But the hope is that it's something nice. Who would have ever expected that these Grassmannians would come up in this story when you're looking at these closed random walks? Like the fact that you got a Grassmannian at the other end is kind of a miracle. So, of course, various people have various ideas of how to sort of generalize, but nobody really has a comprehensive theory of what to do in these more complicated multigraphs.
And when was that done?
Well, so this result is from the 90s. But the connection to polymers is only in the last 4 or 5 years. So the guys that were doing this were, well, one's an algebraic topologist and one's an algebraic geometer. And so they were interested in proving, so the the phrase is they're interested in proving a symplectic version of the Fulton-McPherson correspondence in a particular situation. And so they did that, and they really had no interest in random walks or in modeling polymers. So it took another close to 15 years for people that do care about such things to realize that this stuff actually already existed in the literature and to then start using it. Yeah. Yeah.
Are people able to compute probabilities of these polymers in real laboratory situations and to see if the probability corresponds to the one that you obtained from the Grassmann?
Yeah, so for DNA, it's people can actually, because DNA is charged, you can run it through a gel electrophoresis, and then the idea is that, well, the how fast your knotted DNA will travel through the gel is, empirically at least, seems to be related to the minimum rope length of the knot that it forms. Because the idea is people sort of think that these things sort of form tight knots, and then sort of the surface area is somehow comparable to the rope length. And it's all sort of heuristic. But people actually can run, produce a bunch of knotted DNA and then run them through gels and say, okay, well, the guys that got this far are unknots, and the guys that got this far are trefoils, and the guys that are this far are figure eights, and so on and so forth. And so what you can see is that, for example, there's a preference for, I think one thing that you can say is like there's a preference for chiral knots, there's sort of an anti-preference for alternating knots. There's various patterns that people observe.
Does that, can you tell if that corresponds to probabilities that you obtained from the Grassmann, or is that not refined enough?
At a gross qualitative level, it tends to match. I mean, the problem is, of course, that DNA is actually not literally a random walk, so you have various issues. But at a very gross qualitative level, yes, they tend to sort of match.
Yeah. All right. I guess what I was thinking is there. If you think of some kind of mechanical way, whether it's in a real biological system or not, some mechanical way in which these polymers could be formed, or these random walks could somehow be formed, there would be some kind of natural probability of different types being formed. And does that correspond to the probabilities on the Grassmann?
Well, so
can you?
The short answer is no, because of course DNA is not formed by a random process. Like it's semi-determined. I mean, it's a stochastic but not sort of purely random process. And so the interest in these sort of random walk models is, in fact, to figure out what the baseline of pure randomness is, and then to compare what you actually see with the biopolymers and how it differs from the baseline of purely random, then you hope tells you interesting things about, maybe functional information or something about the process that produced these things. So the answer is no, they don't match exactly. At some gross level, they kind of do.
But your baseline for pure probability is the Grassmannian measure.
Well, another
that's the only one that's really there.
Well, so there is another one, which I'm going to talk about tomorrow. But yes, of what I've said, it's the only one that's sort of there. And so your deviation from that baseline tells you, hope, interesting sort of biological information or physical information. That's sort of the mantra.
So maybe let's, if you have any more questions, let's go ahead and speak after. So people who need to get up can go ahead and go. Let's thank Dr. Shonkwiler.